everyone. So today I'm going to be presenting our recent research effort at Ford to simulate battery material on quantum computer. So why we are interested to simulate battery material? So we are expecting that by 2035, that half of the cars that will be sold in the world are going to be electric. And that's considered to be a very huge challenge for people in automotive industry. These challenges are logistics as well as other related to the performance of the battery itself. In terms of logistics, the battery costs up to from 3,000 to 50K, and that's considered to be almost 60% of the vehicle value. So that is very expensive, and if we need to reduce the vehicle price, we need to reduce the battery cost. Also, this is not just one-time price. We need to replace the battery from time to time. So replacement of the battery is also very expensive. In some car brand, it costs up to 20K. So we need to improve the lifetime of the battery. In terms of the metal, this is also not just an expensive metals, but also we know that we are going to have some shortage of these metals. More specifically, we are talking about nickel and cobalt that goes into the cathode battery material. So in battery, we are expecting that when the scale go up to 1 terawatt hour per year, we are expecting to have almost use 30 to 40% of the current of the nickel production and cobalt production in the world. That, of course, is very problem because 1 terawatt hour means that we can only provide 10 million cars with 100 kilowatt hour. 10 million cars is just only 10% of what we can produce in the world today. So we need to find alternative materials. Also, in terms of performance, two of the most important concerns among consumers, the driving distance and the charging rate. So computational chemistry can play a very important role here to simulate battery materials and help us to improve the battery in terms of energy density, power, cost, lifetime of the battery, and so on. In this case, we can use the theory to design novel materials with tailored properties that we are interested in and have the experiment validate these properties. And that's considered to be very advantage for us because in this case, we are not just reducing the cost, but also it's for environment because we are not wasting metals. And that also will help us to speed up the material discovery. So when it comes to simulate a material, there are various scales. We can go from atomic scales all the way to system. In this work, we are mainly interested in simulating material at the atomic scales using quantum chemistry and simulate and predict the material properties at these microscopic details. Now, the question is, how these microscopic details are connected with those macroscopic details, such as energy density, which improves the driving distance of the battery, or the charging rate. So here is an example of how we connect microscopic details with macroscopic properties of the battery. Batteries are made of two electrodes and electrolyte. During the discharge of the battery, the lithium ion moves from the anode towards the cathode through the electrolyte. And the electron moves through the external circuit to perform an electric work. So by learning about the diffusion of the lithium ion, we can learn about if the material has a good power density or no. And also, by learning about the phase change in this material, we can know what are the, if there's any obstacles that might hinder the diffusion of the lithium ion inside the material and so affect the power density. So by this, we can help to improve the material in terms of charge and discharge rate. Also, another very important problem is the material degradations and thermal and electrochemical stability of the material. And here is where quantum chemistry can play a very important role by simulating the chemical reactions that happens at the interface between the anode and the electrolyte. And that is a kind of the movie you see on the right side. So by simulating this chemical reaction and understand how different, for example, additive in the electrolyte, or how different temperature, or how different if we add any coating the anode or the electrode, how this is, it changes this chemical reaction that happens at the interface, we can help to improve the thermal and electrochemical stability of the battery. And that is really play a very important role to improve the battery performance, and also when it comes to the electrolyte decompositions, which affect the material aging and degradation. So in this case, quantum chemistry can help by understanding those materials at the atomic scales, can help us to improve the material at the macroscopic scale. So how can we simulate these materials? We can simulate this on classical computer. And there exist various methods that can allow us to simulate this material, and it has different scaling. We have the most accurate method that we call it numerically exact, if of course the wave function is complete. It's called the full CI. And this method scales as n factorial. Of course, with the system we are interested in, so battery materials are solid state materials and it's a many body problems, we cannot do this using a method like full CI. Currently, the most practical method is the density functional theory. However, density functional theory has used some approximation, and this approximation doesn't work really well for systems that known in chemistry to have a strong electron correlation. So to understand how this is affected, here I'm showing two examples for battery. So in the figure on the left here, we show the difference between calculated voltage and the measured voltage using different density function theory. And you can see from the figures that the accuracy change based on what function you are using. So from this, for example, this figure here, we see that, okay, the GGA plus U function gives the most accurate results. If you try to calculate using the same function now, but you try to calculate the volume, so in the figure on the right side, we show here the difference between calculated volume and measured volume for the lithiated and dilithiated form of different cathode material. You can see that the function that can predict accurately the voltage does not predict the volume change in the material very accurately. And that is a problem. So from DFT, we always need to know the experiment in advance in order to know which function to use and if this function is reliable or no. And also, this is if we, sometimes you have to use a function that may give you a good results for a given properties, but for another properties, you need to use another function. So this is a problem when we want to discover new material and guide the experimentalist for discover new material to help improve the battery. Because with DFT, we always need to have the experiment in advance in order to know what function to use. So in order to guide the experimentalist, we need to use some accurate method. But accurate methods are interactable on classical computer. And this is where quantum computing comes. So quantum computing promises to bridge this gap between accuracy and efficiency. So how this is work? Here is a very simple example of hydrogen He2. So you have hydrogen with one electron, and when two hydrogen come closer, you form this He2 with two electrons. If I try to describe the wave function for this simple system using a minimal basis set with 4 spin molecular orbitals, now I want to consider all the possible combination of these two electrons in these 4 spin molecular orbitals. And in this case, to describe this on computer, we usually assign the orbital with electron with 1, and the empty one is with 0. And we can then describe the wave function with binary like that. Now, if you try to do this on classical computer, you need 16-bit, because we have the bit is just only 0 or 1. But if you try to do this on quantum computer, you need just 4 qubit because of superposition of this hardware. And that is one of the main one advantage here. We can have this instead of having an exponential for memory, we reduce this into a linear. And when it comes to the code itself, the algorithm, we can take advantage of this interference to design the code, such as in quantum phase estimation, and gain some exponential speed up. Of course, this is not, we are not interested in hydrogen with 2 electrons and 4 orbitals, but we are really interested on this material where we have not just 2 electrons, but have hundreds and hundreds of molecular orbitals. And this is where the quantum computing promises. So At Ford, we are trying at this moment to test existing methods, develop novel ones, estimate resources needed in order to find out how to simulate battery material on quantum computers. And in our recent research, we have been testing VQE method using various unitary coupled cluster ansatz for lithium cobalt oxide, which is known to be a candidate cathode materials for battery. So in the VQE method, as you know, it's a hybrid method that where we design the parameterized quantum circuit on quantum computer, and the parameters of this quantum circuit are optimized on a classical optimizer. And one of the first steps here is the preparation of the initial state. So we know that we are very limited with the quantum hardware now, so we cannot simply at this moment simulate the bulk materials. So we have been trying to use a cutoff model that can mimic this building block of this cathode battery material. And we come up here with this cutoff model, which is made just from 2 formula units. And we choose here 2 models, one with the lithiated form, and one is without lithium after removing 2 lithium and 2 electrons. So to reduce also this further, because the number, if we look at the number of electrons and number of molecular orbital for just this simple cutoff model, it's 150 plus. So we need to find this part in the Hilbert space that we just need to, like has this multi-reference character, and we need to simulate it on the quantum hardware. And to do this, we analyze what's known as the natural orbital occupation number. And it's a very known method in quantum chemistry. And in this case, those orbitals that has a fraction number of electrons, we consider that those are the orbitals that has a multi-reference character. And the other orbitals with integer number, either 0 or 2, those are treated using classical because they don't need any multi-reference method. And from this work, we find that there are almost 10 electron and 20 molecular orbitals that needs a multi-reference character. And for that, we use here in this work, we use 20 qubits on IPM state vector simulator. And this is actually this is noiseless simulator. So this work here, we have done it using Enquanto package, and we have a paper that recently published with this work in arXiv. So what we have been interested in here, we want to know how accurate are those methods to predict the ground state energy for the lithiated and the delithiated model. And why we are interested in that, because if you look here on the left side, when we calculate the voltage of a material, it's calculated using this function here, and this function mainly depends on the energy difference between the lithiated and delithiated form of cathode material or anode, or depend on the material you are interested in. And usually, because these 2 materials has 2 different environments, so you have different oxidation state, the idea of error cancellation is not working in this type of calculation and properties. And that's why method like DFT doesn't work here and usually give some qualitative understanding. And that's why we want to calculate the voltage very accurately, because when you design any material, it's extremely important and that the voltage of your electrodes must be within the voltage window of the electrolyte. If it's not within the voltage window of electrolyte, you have a very strong chemical reactions between the electrode and the electrolyte that cause this kind of instability in the solid electrolyte and cathode electrolyte interface. And that's why we want to calculate this voltage very accurately. And of course, that's if we want to design, like guide the experimentalists to design novel battery material with high energy density to improve the driving distance, we need to give a more accurate result for them. So when we compare the results here obtained by VQE with the classical method, so we compare here the results with the full CI on the active space, we find that on average, the energy difference is within 4 kcal per mole, which is slightly higher than the chemical accuracy, which is 1 kcal per mole. When we compare it with the perturbation method, MP2, we find that it's beyond the chemical accuracy. And we think that there are two reasons might be the reason for that. It could be because we need to increase, add more electronic excitation in the cluster operator, or we, in this work, we start from a single reference. So maybe we need to start from a multi-reference state instead of just a single reference. So that's going to be in future research to explore this more. So the second thing is that we need to calculate and estimate those resources needed to simulate this. And this is very important because of the limitation we have currently on this quantum hardware. So from this here, we have looked at the circuit depths parameters, the number of CNOT gates to simulate this. And what we found that the method using the unitary pair coupled cluster generalized single double give results as good as the unitary coupled cluster single double. But if you look at the number of CNOT gates that needed for this method, it's almost half of the CNOT gates that needed to simulate the same system using the unitary coupled cluster single double. And we think that probably unitary pair coupled cluster could be promising for these near-term devices where we are really limited with the accuracy with the hardware. And this work has been, as I said, done on 20 qubits. Now, if we want, this is a finite system, and for industry, we are interested more for a large system that we want to mimic this bulk material. And so if we try to increase this from 20 up to 44 milliunit, that means that we need 400 perfect qubits. So from these results here and from the resource estimations, we think there are very, the community has a lot of challenges. First, the qubit quality. We know that the qubit today are noisy. They are not perfect. Error rate is between 1 to 0.1% based on what hardware you are using. And that means that because of this rate errors, you cannot execute a circuit that has more than 1,000 two qubit gates. Because if you do this, you will simply get an errors, like you get noise, you get nothing. So the problem is that if we want to use the error correction to suppress this error, we need 1 million physical qubits, and that's not possible today. Then we have the NISQ devices where we deal with the noisy qubits. Now this is we have in this case to use a short circuit, and we might also, like if the circuit is a little bit longer, deeper, you also need the error mitigation. That makes these devices, the quantum advantage is a kind of open questions, because also error mitigations might cause the problem scale exponentially. So the advantage now become open questions, and it's unclear the advantage of this will be for industry application. However, we still think that this is using these tools, it will help us to gain insights as this hardware get matures, because that's all we have now today is the NISQ devices. So from this, I can conclude that, okay, to simulate battery material, we have two ways. We have the classical, but accurate tools here are expensive, and we cannot use it. Or we can use the quantum hardwares, and when this hardware matures, we are expecting to have an exponential speed up. We don't so far observe any quantum advantage, but we think that still this can give us insights as this hardware matures. And once this matures, we think that it's going to be, with this exponential speed up, we might be able to use these devices to guide the development of novel battery materials to improve the battery performance. And with that, I thank you, and I'm open for questions. We are working in this too. We are also trying to find alternative algorithms that might help us to reduce the circuit depths and get more insights and see if this would even possible in the near-term devices. On the other side, also, we want to investigate more on a real quantum hardware. So the work we have done so far is just on a simulator with a noiseless, it has no noise. So we want to still, the idea for us is really we want to get more insights about this hardware. So we want to investigate this more in a real quantum hardware and on a noise simulator in order to understand how noise might affect the accuracy of our problem and get more insight of really whether it's going to be advantage or no. We are not expecting actually, I would say there are a lot more now coming, like more feelings that with NISQ we are not expecting any quantum advantage, maybe some speed up, but not exponential. So how much speed up? We need to investigate on this more, need to develop methods, test how method scales with error mitigations. So it's just really a kind of research at this moment.